All right. Yeah. So really glad to have David from NuCypher over, and NuCypher has been up to some interesting stuff. We've had a great history of hosting NuCypher also at ETH India, starting from 2018, the physical edition in 2018, 2019, and then have seen some cool stuff being built, and yeah, really excited about the direction NuCypher is going in now. And I love that. I love that T-shirt, by the way. Mine is, I wanted to wear it today, but then it's in the laundry because I wear it so much. But then, really cool T-shirt.
Yeah, it's the best.
Yeah.
Okay, so thank you very much, Denver. So yeah, my name is David Nunez. I work for NuCypher, and I want to give you a brief overview of what NuCypher and can you do with it. So NuCypher is essentially a privacy layer for decentralized applications, and we have currently our main offering is Proxy Re-Encryption, which is used for decentralized access control. But let me give you first, just talking a bit about us. So we are a startup that has been working since 2017. We have a previous history as well, but in the blockchain scene, we started in 2017, and basically our vision is that we are focused on improving privacy as a fundamental human right. So we believe the right to privacy must be unconditional, and we want individuals in our society to be empowered and to assert that power in the digital space. The way we do that is essentially through cryptography. That's our business. That's what we do, and in particular, we want to focus on building infrastructure, a service infrastructure for privacy preserving applications. Everything, of course, based on cryptographic primitives that give you mathematical assurance of the privacy goals that we want to achieve. In particular, in the blockchain space, so what NuCypher brings is a layer for data privacy. So applications, either decentralized or centralized, but since we are in blockchain, we focus on this, on the apps. So applications can use NuCypher as a layer for secrets management and access control. And well, essentially that's our goals, and that's what we do. And then specifically, our main offering is access control. So in order to explain this, I'm going to try to go incrementally and give you an example. So imagine you create an application, and now in your application you have a need to share data, but at the same time you want this data to be protected end to end. Now this is a very tricky problem that it doesn't have any obvious solution at all. And on top of that, you want to do that in a way that's both scalable and that's also trustless. So yeah, okay, let's see what you can do. So a bit of cryptography. There is public key encryption and symmetric key encryption and stuff like that. I'm not even covering symmetric encryption here in this idea because as you may know, with symmetric encryption, you have to use the same key for encryption and decryption, which brings the problem of how can you share the same key on both ends. So symmetric encryption is definitely out of the picture. But you know that public key encryption exists. and it's something that exists since almost 50 years. So, okay, why not using it? So imagine you have users like Alice in your application and other users like Bob. So in order to protect Alice's information, you think, okay, let me um, uh, let's encrypt the data with the public key of Alice, and then every time, so the data it's encrypted. So it's initially encrypted with the public key of Alice, and then if I want to share it with some Bob, then I will need to decrypt this data and encrypt it again for the public key of Bob. Okay, that can work for a very simple example with just one Bob, but as soon as you have several Bobs, several recipients, then this doesn't scale at all, because now you will need to perform this process of decryption and encryption again for any new recipient that wants to access. So this basically, as you can see, this doesn't scale. Another problem is that in this solution, Alice's client must be online. So Alice needs to do this hard work of, okay, I have my encrypted data, I need to decrypt it, and now encrypt it again for each recipient that wants my data. So is this type of solution forces Alice to be online, which is it's in most applications it's an assumption that you just cannot make. Okay, so what if Alice just trusts some service? What does this mean? So this means that Alice will outsource what she was doing before on her client side, and now she outsources this to some remote server. But then there's this problem of, okay, now you are trusting some external service without any assurance that there is some um, adversary that can either be just some hacker or something, or a nation state that is compromising your encrypted data, your unencrypted data that is managed in this server. This is even um, more of a problem in a setting like in the Web3 setting, where you have decentralized storage and machines are basically untrusted. They should be assumed as untrusted. Okay, so what can you really do at this point? So this is when our solution comes into the rescue, and it's basically cryptography, pure cryptography. So our solution is based on a primitive called Proxy Re-Encryption. So Proxy Re-Encryption has a very fancy name, but it's essentially just the same public key encryption with an additional functionality. This additional functionality is very cool and basically allows Alice to to create a special key that we call the re-encryption key. And the re-encryption key allows Alice to grant re-encryption capabilities to a proxy. And what does re-encryption capabilities mean? So it means the proxy can take a ciphertext that was encrypted for Alice and transform it to a ciphertext that is encrypted for Bob. And this happens in an atomic way without the proxy being able to get any type of data, neither keys or underlying messages, nothing at all. And the cool thing is that if now a new Charlie appears, Alice only has to create a new encryption key for the proxy. So all the data that was encrypted initially, you don't need to do anything. You just, every time a recipient or a data consumer like Bob or Charlie request access to some encrypted file that was encrypted for Alice, the proxy will simply re-encrypt it on demand. So it's a very nice, simple, and scalable solution for sharing data, sharing encrypted data. So proxy encryption is a very cool primitive that has been lying around for 20 years, and only recently it has started to gain some traction, and especially since we have been working on it. So, okay, and the example I showed you before, this general idea of what's proxy encryption, in this scheme, I'm just showing you one proxy. So this one proxy has, okay, it has some limitations, which, for example, the proxy is a single point of failure, or even though that the proxy is not, doesn't read any kind of data or keys, it has some control in enforcing access control decisions on Bob and Charlie. So you have to trust that the proxy will behave according to the protocol, essentially. So there is really not a confidentiality risk, but there is some availability, let's say, availability risk if you have only one single proxy. And that's when we created this new proxy encryption scheme that it's actually a threshold proxy encryption scheme. So now threshold cryptography primitives are more common, and our scheme Umbral is the threshold way to do proxy encryption. So essentially, it works exactly as I mentioned before, but instead of being one proxy, there are n proxies. So in this drawing, you have 3 proxies, and instead of Bob just going to one of them, Bob will go to the threshold, a threshold number of proxies to get our encryption. So, for example, we can think that this in this example there are 3 proxies, and Bob has to go to and request encryption to 2 of them. So Bob can go to any subset of 2 proxies and ask for encryption, and with the result, Bob basically does some combination process, and just he decrypts the files with his private key on his end. So essentially, threshold proxy encryption is the same. It's just that the internal encryption process is divided into many proxies. Okay, yeah, this is what we call, this is an M of N encryption threshold. So it can be something like 2 or 3, or 3 or 5, or 4 or 4, whatever, depending on your access control needs. Internally, it uses Shamir secret sharing. So this encryption key gets divided into several shares. It also uses a key encapsulation and data encapsulation approach for the scheme itself. And additionally, something that is very cool, in my opinion, it has a very neat non-interactive zero knowledge proof. So proxies cannot just output random garbage, but they, for the encryption output is always together with a proof, with a zero knowledge proof of correctness. So in the event of one of these nodes just lying about the result, the node can get punished. Something that we get asked somewhat frequently is what happens with like, does it matter if you're encrypting a single message or a whole movie or whatever? It doesn't matter, because actually we are doing a key encapsulation, data encapsulation approach. So really what happens inside is the data is encrypted with a symmetric key, and this symmetric key is what's actually encrypted with the proxy encryption scheme. Although our cryptographic library does this in a transparent way, so you don't need to worry about this. But what we can assure you is that the encryption process is it doesn't depend. The proxy encryption part doesn't depend at all on the size of the data that is encrypted. Okay, so that was an introduction to proxy encryption itself as a primitive and how we use it in NuCypher. Now that's the core of the network. But now what's the NuCypher network? So NuCypher network is a set of machines all around the world that give a cryptographic service. So I explained to you before proxy encryption, but we envision many more cryptographic protocols running. So we like to think about our network as a network that provides interfaces and runtimes that are useful and access control, that are decentralized, permissionless, and censorship resistant. So in order you to join the NuCypher network as a node and provide service, you don't need to ask for permission to anyone, and it doesn't matter where you are. You just need to stake in the network. The network is extensible in the sense that we can increase the service offering of the network with more cryptographic primitives. And that's something that I will talk about a bit later. And we have spent a huge amount of time in trying to make our interfaces as intuitive as possible, and our narrative, like how we talk about actors and concepts. So we try to extend this classic narrative of Alice and Bob, these two characters that usually are the example of secure communication. And we have extended this narrative with other characters. So in our network, we currently talk about 4 main characters. So you have Alice and Bob, and there's nothing much to explain about them. So Alice and Bob want to communicate. In this case, Alice wants to share some data with Bob. But the interesting part is that we identified 2 more characters that we implement in our network. One of them is what we call Enrico the encryptor. So usually when you say that Alice and Bob want to share some data, implicitly everyone assumes that Alice is also the source of this data, but that doesn't have to be the case, because recall that proxy encryption is also a public key encryption scheme, which means in order for you to encrypt, you just need a public key, and the public key can be known by anyone. So the important aspect is that once a public key is published and people starts to encrypt data with this public key, only the owner of that private key can decrypt. So Alice is the data owner. Alice is who can decrypt initially everything that's encrypted with a public key, but everyone can encrypt information that's owned by Alice. And we call this character Enrico. And the 4th element in our network is, we call it Ursula. So Ursula is the name that we give to the proxies. Basically, the proxies in the NuCypher network just get encryption keys shares and transform ciphertext from one key to another. Basically, they perform their encryption process. So how can you as users trust that these Ursula nodes will work and will behave? So For starters, that because proxy encryption by itself, it reduces the risks into a level that it's more manageable, in the sense that there is no ability to decrypt any data, and there is no private keys that are disclosed or anything like that. So in the end, nodes only are capable of enforcing access control. And the other part of the equation is that we have a work token, which is the NuCypher token, the Nu. So this is how a token that's not used in payment, but is used by nodes as a deposit, as a collateral against the potential malicious behavior. So essentially, if you are a node and you are behaving correctly, that's great. But if you are misbehaving, you will get slashed and you will get punished. And also, because there is a zero knowledge proof that gives you assurance that the encryption process is correct. Okay, so I explained many of the concepts, and this is how everything fits into the picture. I'm going to explain the part that's below in more detail later, but the part that's above is the Ethereum blockchain. So the NuCypher network currently works on top of Ethereum. So the NuCypher token, it's an ERC20 token, and we have several smart contracts that govern the rules of our network, and all of them are Ethereum smart contracts. So apart from the cryptographic and data sharing steps that are in the lower half of this picture, in the upper half, the Alice actor needs also to interact to the blockchain, because when you create what we call a policy, which is an access control decision that is written to the blockchain, you need to pay for it, and you need to escrow a fee, essentially a fee that the network will earn, the nodes will earn with time. So yeah, that's the other part of the NuCypher network I wasn't explaining, which is how the nodes are governed, and how the nodes like have some consensus on the rules. Okay, and now for the lower half, I always like to use an example. So in this example, let's assume that the use case is that Alice wants to encrypt. So Alice has encrypted data, which is encrypted data about healthcare information of hers, and she wants to, at some moment, she wants to give access to a doctor, okay, which is Bob in our narrative. So one of the cool things about NuCypher and Proxy Re-Encryption is that Alice doesn't need to do anything in preparation for data sharing. Alice can just start by generating a public key, and using this public key, either herself or anyone can use it. So in this example, we are going to imagine that he has a heart monitor, like some sort of uh, uh, clock that watch, sorry, some sort of watch that um, measures her heartbeat, and that this device is capable of public key encryption. So this device will take the public key of Alice and encrypt her heartbeat information, and send this information to some storage layer. It doesn't matter for NuCypher, from the NuCypher perspective, it doesn't matter at all what kind of storage are you using. You can use centralized alternatives like Amazon or Google or whatever, But you can definitely use decentralized services like IPFS or Swarm or Arweave or whatever. So this is very cool because data is being generated and encrypted, and at this moment, only Alice is capable of decrypting it. At this moment in this picture, Bob hasn't appeared yet, but then at some moment, Bob requests access to Alice, and Alice will create a policy. And this policy, for this to happen, she would need to interact with the NuCypher network and essentially tell the network, okay, I want to give access to this Bob, take this amount of ETH as fees, and take these re-encryption keys, essentially. This is done by the NuCypher client, so Alice actually doesn't need to do much. And then the NuCypher network now holds capabilities of re-encryption. And now Bob only needs to fetch pieces of encrypted data that initially is encrypted with Alice's public key. And now, since he wants to open it with his own private key, go to the network and request for encryption. And if everything is correct in the network, in the sense that is this Bob really authorized, and is this policy paid for, and stuff like that. So assuming that everything is working fine, Bob will get re-encryption of the original ciphertext, and he will simply be able to open it with his private key. So I want to stress what are the characteristics that made the NuCypher solution unique. One is that Alice can create public keys before knowing who are the potential consumers. So she can have, in this example, she has one heart monitor, but she could have 30 different devices encrypted information with different public keys that she controls. And she still doesn't know who is going to share this information with. And that's fine. That's one of the great things of Proxy Re-Encryption. Also, for these data producers, like the heart monitor, they don't need to be aware at all of the recipients. So they just need to encrypt for Alice, because Alice is the owner of the data. So that's what another cool thing about NuCypher is that encryption is completely decoupled from data sharing. Basically, both things happen at different times and are completely independent. Now, another cool feature is that Alice never interacts with the doctor, with Bob. She only needs to know his public keys. That's the only thing that she needs to know, but that's it. They don't need to communicate, or they don't need to exchange any kind of information. Alice also only has to interact with the network when granting access. So she can grant access to the doctor, and then for as an extreme case, she can disappear completely from the face of the earth, and that's fine. And the doctor will never interact with Alice or the heart monitor. He only needs to get the ciphertext and the metadata about some policy metadata. That's all. Okay, so that's essentially how NuCypher works. Now some specific facts about the network and our development. So we are live. We've been live since October 15. We started with a novel token distribution model that we call the word lock, and that this allowed people to stake ETH in order to run a node. And it was a great success. We have more than 2,000 nodes and more than 350,000 ETH stake in our Warlock contract. And it's been working. The Warlock mechanism has worked great for token distribution. And And on the development side, what's next for us? So obviously scaling. Um, there are several transactions that are happening on the NuCypher network. So Alices will create policies and nodes will stake, and they also have to perform some sort of check-in transaction. And this is all paid on with ETH, with gas. And we all know that gas prices are just crazy. Um, Although last month has been pretty good, but I mean this screenshot from February is completely it's a disaster. So we're working on solutions on layer 2 for scaling. And but what's more exciting for us, I think, at this moment are two things. One is uh, native browser support. So NuCypher is currently only supported with the Python client and through JSON RPC interfaces. We have some partial support, browser support through native messaging, but um, we certainly lack of a complete and simple and accessible browser support. So we're starting with a Rust backend that's I'd say is experimental in the sense that it's very recently developed, but it's working completely. And the cool thing is that it's compatible with JavaScript. So from this, we are developing more connectors on the JavaScript side. So hopefully, very soon, NuCypher can be used directly 100% in the browser. And the other thing that we are pretty excited about is to extend our network. Um, I don't know if you have heard about the project Keanu, which is a decentralized um, merger that's happening with the Keep network. So the Keep network is also another decentralized network that provides threshold services. In this case, they have been focusing on TBTC, which is a non-custodial um, solution for tokenized BTC on Ethereum. And together with our proxy encryption offering, we are offering a new network, which we still don't have a name, but we call it Keanu for the moment. And we're pretty excited about it because it will bring new services for stakers. But apart from that, we have some internal new developments, like we are working on distributed key generation for proxy encryption, and we have some very promising work started. And also there are some cross-chains services for NuCypher. So there is an independent team working on making NuCypher work on Polkadot, and another one for Cosmos. So that's something very interesting for us as well. And we always like to think about what other cryptographic things we can bring to the network. Okay, now before ending, just for the hackathon, we would love for you to build something on NuCypher. These are just a selection of ideas. We are particularly interested in seeing something like in-game end-to-end secrets. Like we always talk about it, but we never like there are not much um, proposals on this side from participants. So we would love to see something like that. But I mean, there are many different applications that you can build, like encrypted video streams or stuff like encrypted OnlyFans or integration with wearable devices. I don't know. I mean, the sky's the limit in just any kind of application that needs some encrypted data sharing. It's a good target for building with NuCypher. So, okay, that's it. We have a Discord server. We are there all the time. Please join the server and talk to us. We will be very happy to see you guys on our server. And you have here some examples, some links to some documentation on NuCypher, and that's it. Good luck with the hackathon, and I hope you enjoy this talk.
Yeah. Yeah, really cool stuff there, David. Just a personal question that I had. Could you just elaborate a bit more on what you mentioned about in-game encryption? Like, what could you give an example there? Wanted to kind of understand.
Right. This is something that it's a proposal by one of our team members, um, Justin Miles, that he envisions why games don't include something like loot boxes that are really encrypted, like the content on the of the box that let's say it's a box like in Super Mario, right? We even had at some moment we have a demo that showed like a sort of Super Mario and a box, and this box had a secret. It can be some gadget where in the game, but the secret is it's some data that's actually encrypted, and you open it using NuCypher. So that's something that it's not it's not there. I mean, actual end-to-end encryption inside games, something that has not been exploited, and I don't know why. And but I mean, I guess that there are many other applications of end-to-end secrets inside games. I'm sorry because I don't play video games at all, so I cannot give you like many ideas, but I remember particularly distinctly this idea of secrets inside loot boxes. Yeah.
Yeah, for sure. And I think a lot of interesting applications there, and there's already a great user base of consumers. So kind of perfect application there. Right. Have some questions. Just two questions, I think. Do you want to just type out the answer, or do you want to answer them live?
Yeah. So I see. What's the main advantage of moving the encryption part for the from the data owner to the proxy? Okay, I think maybe there is some small misconception here, because the encryption will never happen on the proxy side. The proxy just encryption already always happens end to end. What we were trying to say is that encryption doesn't need to happen on Alice's side, but she can give public keys to anyone, and anyone can encrypt. But once data is encrypted on one end of the picture, then these ciphertexts are encrypted for Alice, and the proxy will transform the ciphertext. It's like the proxy has some magic ability to take a ciphertext for Alice and transform into a ciphertext for Bob. But the proxy doesn't encrypt information. The proxy just transforms information, and that's the re-encryption process. And the other question is, are there any loopholes in the process? I don't know exactly what when at what stage of the process Shiraz refers to, but I imagine in general to the proxy encryption data sharing, and there are no loopholes really. So Alice will own some sort of public and private key. Bob will have also a public and private key. The proxy has this special key called the encryption key that doesn't give him give the proxy any capability for decryption or for reading data. And at no point these keys will leave those domains. And the only data that is communicated is always are ciphertexts. So really, there's no way to make a loophole in this game. So yeah, I guess okay. Okay. Yeah, there is a follow-up question. So re-encryption, what re-encryption does is it's not like an added layer of security. It's more like, imagine you have data that is encrypted with some key, right? And now you want to share this data. So if you think about it, using traditional techniques, there is really no secure way to share data that is already encrypted. So what usually happens in this solution is that you either have to decrypt the data and encrypt it again, or you have to share the encryption or the decryption keys with someone. The someone is usually a trusted party, but we don't want third parties getting into the picture, right? So this is what happens with Google Cloud and sorry, Google KMS and Amazon KMS and stuff like that, where they in theory they have in a very difficult and extreme case, but they have decryption capabilities because you are trusting with your keys in order for them to be able to to provide some KMS like sharing functionalities.
All right.
Okay.
Yeah, I think you've answered all the questions. There was one other question. I think you've already answered it. Does re-encryption happen off-chain or on-chain? That's
Okay, I don't see. Oh yeah, does encryption happen? Yeah, it happens off-chain. Yeah, on NuCypher we are the cryptographic part is blockchain agnostic actually. So everything happens off-chain. Yeah.
all right. Cool stuff, David. Really looking forward to things being built with NuCypher at ETH India again.
Okay, thank you for having me and good luck for the hackers.
Yeah, thanks. Thanks a lot, David. Thanks for joining in.
Thank you.
Have a great day.
You too.
Bye-bye.